Hi there, my name is Parun Rao. We are from P2 Group 2. Our title is Filter Design of Noise for ECG Signal. What must we do? We need to design a filter to remove a power line noise corrupting an ECG signal using MATLAB. Power line noise is a electromagnetic fields caused by a power line represent a common noise source in the ECG. It is necessary to remove power line interference, which is always about 50 to 60 Hz frequency from ECG signals, as it is completely superimposes the low frequency ECG waves. We have chosen FIR filter for this design. These are the graph for the continuous plot and discrete plot in MATLAB. So we can see there is 2000 samples, which is an amplitude versus time graph. And for continuous, we use plot syntax, and for discrete plot, we use stem syntax.
Okay, I will continue this presentation by presenting to you about the miniaturized response plot. Basically, a miniaturized response plot will be used and serve three different purposes depending on at which the miniature plot is produced. As for the miniature response for the input, it is used to identify the noise frequency of the original signal. The miniature response of the output is used to check and examine whether the noise is eliminated or not from the original signal. It will show which frequency is preserved and which will be filtered out. And last, for the filter, the miniature response will be used to determine characteristic of the filter consisting of the passband or stop band frequency of the filter. Okay, this is the full plot miniature response of the input. As we could see here, at frequency 50 Hz and also 150 Hz, there is a spike that indicates the existence of noise in the signal. The filter that will be designed will have a cut-off frequency around this value. Okay, that's all from me.
So this is the FIR filter that we designed by using a low pass filter with semi-window method. This is the MATLAB code to generate the filter. The filter order is set at 300. As the higher the order, the steeper the roll off rate, and it gets similar to the ideal filter properties. The low pass filter with normalized cut-off frequency is set at 0.4, as we want to preserve the signal below that frequency and remove the noise occur at frequency 0.5. The filter is designed by using the filter visualization tool, and below are the magnitude response and the impulse response that we obtain. And the impulse response obtained is causal.
Next, we use roots to find the coefficient b. After acquiring the b coefficient, the function z-plane is used to obtain the zero-pole plot. As can be seen from the figure, the system is a second-order system, therefore there are 2 poles and 1 zeros. By using the low-pass filter, the power noise has been successfully filtered. Figure on the right-hand side is the continuous time domain filtered signal, while the figure on the left-hand side is the magnitude plot for the filtered signal.
Assalamualaikum, my name is Mazlim Mizura. So I will be presenting the FIR design using bandstop filter. So this particular filter rejects a particular range of frequencies and eliminates unwanted noise that can give a stable output. So this bandstop can reject filter cut or reject frequencies that are not within a certain range. So this is the result that we simulate in the MATLAB using the code HD1 equals to dfilt.dffir filter. This is the magnitude response in dB. Thank you.
We use the rules to find the B coefficient of the filter and using the Z-plane to determine the zero-pole plot. Since it is a 100 order bandstop filter, so it has 100 poles and 1 zero. By using the bandstop filter, only the signal before the 50 Hz and after the 150 Hz has been passed and the power line noise has been filtered. There is the coding to plot the magnitude plot and the continuous time domain plot for the filter signal.